Let's next study some simple two-dimensional potential flows that could be used to construct more complex flows. The first flow we consider is a uniform flow where the velocity at every point is the same, v naught, and the velocity vector is inclined at an angle theta to the x-axis, so that the velocity in the x direction, Vx, is v naught cosine theta, and we give it a symbol capital U, and the velocity Vy in the y direction is v naught sine theta, which is given a symbol V. Then phi, the velocity potential, is simply capital Ux plus capital Vy, that is v naught x cosine theta plus v naught y sine theta. And the corresponding stream function is minus Vx plus Uy. This is the flow net. The solid lines represents the stream lines, the lines of constant psi, and the broken lines are the potential lines, the lines of constant phi, constant velocity potentials. This is not very interesting in itself, but will be used for building up flows past bodies in two dimensions. The next flow we take up is the source or the sink flow. Laplace equation del square phi is equal to 0 in two-dimensional cylindrical polar coordinates is 1 over r del by del r of r del phi by del r plus 1 over r square del square phi by del theta square is equal to 0. For axially symmetrical flows, the derivative with respect to theta are 0, and so this equation reduces to 1 over r del by del r of r del phi by del r is equal to 0, which is readily integrated to give a solution. Phi is equal to C1 ln r plus C2, where C1 and C2 are constants. Just like stream functions and velocity potential, we can add an arbitrary constant to any of the velocity potential and stream functions, because it's only the difference of the stream functions or the gradient of velocity potential that matter. So we can set C2 as 0, and then the velocity potential is constant times ln r. This is the fundamental solution of Laplace equation for two-dimensional axisymmetric flow. Now, this potential function gives you the r velocity component as del phi by del r is equal to c by r, varying inversely as radius, and v theta as 0. So velocity is radial outwards for c positive and inwards for c negative. So the velocity vectors are like these. For source flow, when c is positive, and inwards if c is negative. If we find out the total flow, total volume flow crossing a circle of radius r. We can obtain it by integrating the r component of velocity multiplied by r d theta over theta from 0 to 2 pi, and we get this value as 2 pi c. We can treat this total volume flowing out as the source strength Q, such that C becomes Q divided by 2 pi, and the velocity potential phi can be given as Q divided by 2 pi ln r, as the velocity potential for a source of strength Q per unit depth for two-dimensional flows. Using Cauchy-Riemann conditions, that is del phi by del x is equal to del psi by del y, and del psi by del x is equal to minus del phi by del y, we can obtain the stream function for the flow as psi is equal to q divided by twice pi theta. These are the streamlines that are plotted for q is equal to 1, that is for a unit source strength. This line here is for psi is equal to 0. We go around, we reach here. This is for psi is equal to 0.25. And we come back, we give the whole circle. We have this line which represents psi is equal to 0 as well as psi is equal to 1.0. These are the streamlines for a source flow. Velocity outwards for a source and the velocity inwards for a sink when the value of q would be minus 1. Let's next do what is called a line vortex or a free vortex. We have seen earlier that free vortex is the name given to a swirling flow in which there is no rotation of the fluid element. Two particles are shown with same orientation throughout the motion. The particles are not rotating about their own axis, but their different velocities in the two circuits, both the angular velocity as well as the linear velocity. The radial component of velocity Vr is 0 in this case, and the swirl component V theta is a function of r alone. So swirl component is not a function of theta. The Laplace equation for the velocity potential in 2D cylindrical polar coordinates reduces to del square phi by del theta square is equal to 0. And the fundamental solution is phi is equal to c theta up to an arbitrary constant, and which gives the velocity component v theta as 1 over r del phi by del theta as c divided by r. So the swirl component of velocity is inversely as r. Fastest at the center and slowest outside. We evaluate the circulation about a circular circuit of radius r in this flow, and we get the circulation is equal to twice pi c independent of the radius of the circuit. We have chosen circular circuit of radius r and find out that our cancels out, and the circulation gamma is obtained as independent of 2 pi c. Therefore, gamma can be used as a strength of the free vortex, so that in the expression of the velocity potential that we have, c theta, we could replace c by gamma by 2 pi. And if we do so, the velocity potential becomes gamma theta divided by 2 pi. The radial component of velocity is 0. The sole component of velocity is gamma by twice pi into 1 by r, c by r. By using Cauchy-Riemann equations, we can obtain the stream function, and stream function psi is minus gamma by twice pi ln r. So these are the streamlines and potential lines for a free vortex. The solid lines are the streamlines. The velocity tangent to the streamlines counterclockwise for positive value of gamma and clockwise for the negative values of gamma. The radial lines are the equipotential lines or the potential lines. Now, we have seen earlier that in rotational flows, the Bernoulli equation is applicable between any 2 points in the flow field. And therefore, for a free vortex, if we take a point 1 at radius r1 and a point 2 at radius r2, then the pressure difference P2 minus P1 is obtained as minus gamma square by 8 pi square into 1 by r2 square minus 1 by r1 square. If r2 is less than r1, then this quantity is negative. That means pressure P2 at the inner point is much less than pressure at the outer point. This is the shape of the pressure distribution. Pressure far away at r tending to infinity is shown by the broken line, and then the pressure decreases as r decreases. The vortices are very common in nature. They're found in oceans as whirlpools, in the atmosphere as tornadoes. They're huge vortices in the ocean. One of the largest one is located close to the Arctic Circle in Norway. It is estimated that 400 million cubic meters of water passes in a narrow strait during this event. This occurs regularly because of the lower pressure towards the center of this vortex. The water level decreases, so it produces a kind of a hole. This is an underwater view of the same vortex. What you see here is an air cone that seems to be pointing downwards towards the ocean floor. In the atmosphere, these whirlpools appear as tornadoes. A tornado is a violently rotating column of air in contact with the ground underneath a cumuliform cloud and is often visible as a funnel cloud. the pressure is very low in this funnel, and so it sucks the debris, cars, and human beings up. The intense low pressure caused by the high speed wind and the rapid rotation of water vapor in the air condenses into a cloud droplets due to adiabatic cooling. This results in the formation of a visible funnel cloud or a condensation funnel. So let's summarize the three basic potential flow solutions that we studied so far: a uniform flow, a source flow, and a free vortex. We will build up the solutions of more complex flows from these basic flows in the next lectures. Thank you.